Ever feel like the internet is this giant buzzing machine and we're all just trying to figure out how the different parts, talk to each other?
Definitely.
Well, a huge part of that communication happens through REST APIs. But just like any busy place, there's also a growing risk of things going wrong, security-wise.
Yeah, that's a big concern now.
It's kind of alarming when you see reports like Google Cloud's 2022 findings
Right.
saying over half of organizations had an API security incident in 2021. Makes you think, right?
It absolutely does.
Yeah.
And these APIs, they're really the fundamental building blocks of modern web apps. So making sure they're secure and that communication is clear and well managed. It's not just a nice to have, it's critical.
Right, it's the foundation.
Pretty much, yeah.
Yeah.
How so much of our digital world actually works.
Okay, so for this deep dive, our mission is pretty straightforward. We're going to dig into our sources and pull out the most important stuff you need to know about, well, REST API authentication, how to handle errors effectively, and the best ways to manage different versions of your API. Think of it as getting the essential knowledge without having to wade through all the technical weeds yourself. We want to get you informed quickly and thoroughly.
Precisely. Consider this your rapid onboarding to some of the most vital aspects of building and using web applications. We'll break down everything from, the initial handshake of authentication to how to gracefully deal with problems
Yeah.
and how to evolve your APIs without breaking everything for your users.
All right, let's jump right into it then. Let's talk about getting through the front door, authentication. What exactly is REST API authentication in simple terms?
Okay, so in essence, it's about verifying who is trying to access your API.
Verifying who?
Yeah, it's the process of confirming their identity
Right.
so you can then decide if they have permission to see or do what they're asking for. There are really three core goals. First, confirm who they are.
Right.
Second, allow authorized access. And third, crucially, keep the unauthorized people out. It's kind of like showing your ID to get into a secure building.
So authentication is proving who you are, and then authorization is checking if you have the right to be there and do stuff.
Exactly. Perfectly put. Authentication confirms identity. Yes, you are who you claim to be. Then authorization steps in to determine, based on that identity, what specific things you're allowed to access or do.
Like a consult ticket example you mentioned earlier, authentication gets you in, authorization says where you sit.
Yeah, that's a great way to think about it. Authentication gets you past the main gate.
Yeah.
Authorization checks your seat number.
Got it. Okay, so what are some of the common ways this ID check happens with APIs? I remember seeing basic authentication mentioned in the sources.
Yes, basic auth. It's one of the most fundamental methods. It's basically where the client sends their username and password inside the HTTP headers with every single request.
Every request, okay.
Yeah, the browser or the application takes a username and password, puts a colon between them, so username.password, and then it encodes this whole string using base64.
Base 64, okay. So that's making it secure, is it?
Not exactly. That's a common misconception. Base64 is just an encoding scheme. It's not encryption.
Oh.
It's more like, translating it into a different alphabet. It looks scrambled, but it's actually pretty trivial to decode back to the original username and password.
Okay.
So the server gets this encoded string, decodes it, and then checks if the username and password match what it has stored. If not, it typically sends back a 401 unauthorized error.
Sending my password like that, even encoded, doesn't sound super safe, especially if it's easy to decode.
You're right to be concerned. The major vulnerability with basic auth is if you're not using HTTPS.
Right, the secure connection.
Exactly. Without HTTPS, that base64 string with your credentials is just sent in plain text over the network. Anyone listening in could potentially grab it and decode it very easily.
Yikes.
Yeah. So because of this, we strongly advise against using basic authentication for anything sensitive or really in production environments, unless you absolutely have HTTPS enforced everywhere. And even then, there are generally better, more secure options available.
Okay, so basic auth, simple, but probably not for important stuff.
Got it. What about API keys? I see those used quite a bit.
Right, API keys are another common one. They're essentially unique, usually long alphanumeric codes that are assigned to a specific client application. Think of it like a digital key card, but for an app, not a person.
Okay, a key card for the app, and how does the app get this key?
Developers usually get them by registering their application with the API provider, often through a developer portal or some kind of sign-up process.
And once they have a key, how do they, present it?
Good question. The API key needs to be included in every request the application makes to the API. There are a couple of standard ways. Sometimes it's put right in the URL as a parameter, like that API key or key.
Mm-hmm.
But more commonly and generally preferred is to include it as a custom header in the HTTP request,
Yeah.
something like API key.
Right, so the server then looks for this key in the request and checks if it's one that it recognizes and trusts. Exactly. When the API server gets a request, it pulls out that API key and checks it against its list of known authorized keys. If the key is valid, the server then usually does an authorization check.
Ah, authorization again.
Yep, to make sure that the specific application tied to that key actually has permission to access the resource or perform the action it's trying to do.
Are API keys only for security checks like that, or do they have other uses?
They're actually really useful for rate limiting too.
Oh, right, to stop apps from overwhelming the API.
Precisely. It lets the API provider control how many requests a particular app can make in a certain time period, like, say, 100 requests per minute. It helps prevent abuse, ensures fair usage for everyone, and protects the API infrastructure.
Makes sense. And how do you keep the API keys themselves secure? Seems like if someone else got hold of my app's key, they could pretend to be my app.
That's a critical point. Security hygiene for keys is vital. One really good practice is key rotation.
Changing the locks periodically?
Exactly like that. Regularly generating new API keys and disabling the old ones limits the damage if a key does get exposed somehow. And again, just like with basic auth, using HTTPS is absolutely essential.
Always HTTPS.
Always. It encrypts the whole communication, including the API key, so it can't be easily sniffed out during transmission.
So API keys seem like an improvement over basic auth, definitely, but they still have some weaknesses if not handled carefully.
That's a fair summary. The main limitation is that if the key isn't kept secret by the application developer, like if they accidentally commit it to public code repository or embed it in client-side JavaScript,
Oh, yeah, that happened.
it does, then it can be relatively easily discovered. So for more sensitive applications or where you need finer-grained user permissions, token-based authentication is often a better, more robust approach.
Okay, token-based authentication. That sounds a bit more complex, but maybe more secure.
It is a bit more involved under the hood, yes, but it offers significant advantages, especially around security and efficiency. With token-based auth, the client first sends its credentials like username and password to the server once.
Just once.
Just once to get the token. If the credentials are valid, the server issues the client a temporary token. It's like getting a temporary pass. Then, for all the following requests, the client just sends this token in the HTTP header instead of the username and password.
Ah, okay. That sounds much better than setting the password every time. How does that actually look in practice, like in the code example?
Right. Remember that Python requests snippet,
Mm-hmm.
python.importrequests.url, https.example.com,
Yeah.
URL.
Bearer access token requests.getURLHeaders.print response.status code, that access token part. That is the token the server gave the client. The important bit is the authorization, bearer.header. Bearer is a standard scheme indicating that the request carries a bearer token, basically. Whoever bears carries the token is authorized.
Got it. Bearer token. So I get this token once, and then I use it for a while. But you said it's temporary. What happens when it gets old?
Exactly. Tokens have an expiration date. This is a crucial security feature.
Why is that?
It limits the lifespan of a token if it ever gets compromised. If someone steals a token, they can only use it until it expires. Once it expires, the client has to get a new one from the server.
How does it get a new one? Log in again?
Sometimes, yes. Or in many systems, especially with OAuth 2.0, which we'll get to, the client might get both an access token and a longer-lived refresh token. When the access token expires, the client can use the refresh token to get a new access token without the user having to log in again.
Okay, that makes sense. So again, HTTPS is vital here, I assume. And maybe the
Right.
token itself is encrypted or something.
Absolutely. HTTPS is non-negotiable for transmitting tokens. And yes, for production systems, you typically use standards like JWT, JSON Web Tokens, or the OAuth 2.0 framework. These provide standardized ways to structure tokens, often include digital signatures to prevent tampering, and manage the whole token lifecycle securely.
You've mentioned OAuth 2.0 a couple of times now. It sounds like a
Mhm.
big deal in this space. Can you dive a bit deeper into what makes it special?
Yeah, OAuth was really significant. What's particularly interesting is that it's not just about authentication proving who you are, it's primarily an authorization framework.
Authorization, what you're allowed to do.
Exactly. It's a widely adopted standard that lets users grant limited access to their resources on one service, say their photos on Google Photos, to another application, like a photo printing service, without ever giving their Google password to that printing service.
Ah, okay. Like when I let a fitness app connect to my Spotify account to play music during workouts, the fitness app never asks for my Spotify password.
Precisely. That's a perfect example of what OAuth calls delegated access. The user delegates specific permissions to the third-party app.
Okay.
OAuth 2.0 defines several ways this can happen, called grant types, depending on the kind of application and the situation. There's the authorization code grant, very common for traditional web apps. The implicit grant, often for single-page JavaScript apps. The client credentials grant for machine-to-machine communication. And the resource owner password grant, which is generally discouraged now because it involves handling the user's password directly.
Can you give a quick sketch of how that authorization process usually flows? It sounds complicated.
It can seem that way, but the basic idea is this. First, the application you're using, the client, redirects you to the service where your data is stored, the authorization server like Google or Spotify.
Okay, I get sent away for a moment.
Right. You then log in directly with that service if you aren't already. Then the service asks you, do you want to allow this client app to access specific permission, for example, your playlist?
The permission screen, yeah.
Exactly. If you click Allow, the authorization server sends you back to the client app, but with either a special, short-lived authorization code or sometimes directly an access token. If it sent a code, the client app then secretly exchanges that code with the authorization server to get the actual access token.
Okay.
Finally, the client app uses that access token, putting it in the authorization bearer header we talked about to make requests to the resource server, like the Spotify API, to access your data on your behalf.
Wow, okay. That is quite a few steps. Lots
Yeah.
of redirects and different codes and tokens flying around. What's the main downside of using OAuth 2.0 then? Sounds powerful, but maybe tricky.
You hit it right there. The primary challenge with OAuth 2.0 is its complexity. Because it's designed to be flexible and handle many different scenarios, setting it up correctly and securely can be quite involved. It requires a good understanding of the flows, the potential security pitfalls, and the different grant types.
Gotcha. Powerful standard, but definitely not simple to implement from scratch.
Definitely not trivial, no.
Okay, we've covered a few different ways to handle authentication: basic, API keys, tokens, and the big one, OAuth 2.0. If we zoom out a bit, what are some overarching best practices we should keep in mind for API security in general? Just a quick rundown.
Sure. Key takeaways for security. First, always enforce TLS HTTPS. Encrypt everything in transit.
Yeah.
For single sign-on, SSO, using OAuth 2 combined with OpenID Connect is generally the way to go. OpenID Connect builds on OAuth 2 to add identity information.
Okay.
Regularly rotate and invalidate your access tokens and API keys. Implement rate limiting to prevent brute force attacks and denial of service. Try to centralize your authentication logic. Don't scatter checks all over your code.
Yeah.
Avoid hard coding any credentials or keys directly in your source code.
Big no-no.
Huge no-no. Use API keys thoughtfully, mainly for programmatic access for known users or services, and make sure you have solid secrets management practices for storing and handling those keys securely, like using a dedicated secrets manager.
Okay, that's a really good checklist for keeping the front door locked tight. Now let's switch gears. What happens when things don't go according to plan? Let's talk about errors. How should we handle errors in our REST APIs?
Right. Proper error handling is absolutely vital. It's not just about catching bugs, it's fundamental to creating a usable and, frankly, developer-friendly API.
Developer-friendly, meaning the person trying to use the API.
Exactly. When something goes wrong with their request, you need to give them clear, informative feedback. Tell them what went wrong, and ideally, give them a clue about how they might fix it.
So it's definitely not enough to just send back a response saying error occurred.
Oh, definitely not. That's incredibly frustrating for a developer. The foundation of good error handling in REST is using the correct HTTP status codes.
The numbers, like 404 not found.
Exactly. Those codes are standardized and fall into 5 main categories. 1XX are informational, 2XX means success, 3XX are for redirection, 4XX indicate client-side errors, something wrong with the request.
Like the 404.
Right. Or 400 bad request, 401 unauthorized, 403 forbidden.
Yeah.
And 5 mistes codes mean server-side errors, something went wrong on the API's end.
Like 500 internal server error.
Precisely. These codes give the client an immediate high-level understanding of what happened. Was it their fault, 4XX, or the server's fault, 5mixx?
Okay. So what are some specific error codes that are really important to use correctly? You mentioned a few.
Yeah, some key ones are 400 bad requests. The request itself was malformed. 401 unauthorized.
Hmm.
authentication is required and failed or wasn't provided. 403, forbidden, authenticated but not allowed to access this specific thing. 404, not found, the requested resource doesn't exist.
Mm-hmm.
Then there's maybe 412, precondition failed, sometimes used for things like optimistic locking conflicts. And on the server side, the main ones are 500, internal server error, a generic something broke on the server, and 503, service unavailable. The server is temporarily down or overloaded.
Okay. The source material mentioned trying to minimize using that 500 internal server error code when responding to clients. Why is that?
Good point. Because the 500 error is basically a shrug from the server. It just says, oops, something unexpected happened on my end, but it gives the client zero information about what went wrong.
Right. Not very helpful for debugging.
Not at all. It makes it really hard for the client developer to figure out if they can do anything about it or if they just need to wait or report a bug. So the best practice is to try and handle or catch those internal server issues whenever possible and respond with a more specific status code that actually reflects the underlying problem.
Like if the server couldn't find a record in its database needed for the request.
Exactly. Instead of letting that crash and result in a generic 500, your code should catch that record not found situation and deliberately return a 404 not found error to the client. That tells them the resource they asked for doesn't exist, which is much more actionable information.
That makes total sense. Be as precise as possible with a status code. But sometimes even the right code, like 401, might not be enough info on its own, right?
Exactly right. Often you need to provide more context in the actual body of the HTTP response, usually as a JSON object.
Okay, so what should go in that JSON body?
Common practice is to include a few fields. Maybe an error field with a unique application-specific error code. This isn't the HTTP status, but your own internal code, like auth0001.
Mm-hmm.
Then a message field, which is a brief, human-readable summary of the error, and often a detail field that can provide a longer explanation, more context, or specific information about what was wrong with the request.
Can you give an example? Say, for that 401 unauthorized.
Sure, if someone tries to log in with the wrong password, you'd send the 401 status code, and the response body might look something like this: JSON error, auth-0001 message, incorrect username or password, detail. Authentication failed. Please ensure the username and password provided in the request are correct. Detail.
Ah, yeah. That's much more helpful than just getting a 401 status code back. The sources also mentioned an optional help field.
Yes, that's another good practice. You could include a help field containing a URL that points to documentation. Maybe a page explaining that specific error code, auth00001, in more detail, or offering troubleshooting tips.
Nice. What about reporting multiple errors at once? Like if a form submission has 3 invalid fields.
That's possible too. Some APIs structure their error responses to include a list or array of error objects, maybe under a key like errors. Each object in the list could detail as a specific problem.
Mm-hmm.
It can be useful for validating complex inputs, but for simpler APIs, it can also add complexity. Often just reporting the first or most significant error is enough.
Okay. Are there any established standards for how these error response bodies should actually look to make them consistent across different APIs?
Yes, there is. The IETF, the Internet Engineering Task Force, defined a standard called RFC 7807, titled Problem Details for HTTP APIs.
RFC 7807, okay.
Yeah. It provides a standard JSON structure for error responses. It defines several key members, or fields type, which is a URI that identifies the type of error. Think of it like a category link. Title, a short, human-readable summary. Status, which is the HTTP status code itself. This is optional, as it's already in the headers, but often included.
Mm-hmm.
Detail, a human-readable explanation specific to this occurrence of the problem. And instance, another URI that identifies the specific occurrence of the error.
So it's like a more formal, standardized way of providing that info we just talked about. Type, title, status, detail, and a unique identifier for this specific problem instance.
Exactly. And the use of URIs for type and instance is pretty neat. The type URI can actually link to documentation about that error category. The instance URI could potentially point to logs or other diagnostic info about this specific failure, though that's less common in public APIs.
Okay, so using RFC 7807 makes your errors more predictable and potentially self-documenting.
Precisely. While adopting RFC 7807 isn't mandatory, it brings consistency and helps clients build more robust error handling logic because they know what structure to expect. It's definitely a good practice to consider.
The sources gave some examples from big APIs like Twitter and Facebook. What did their error responses look like? Do they follow this standard?
Well, the example showed some variations. Twitter's API for an unauthenticated request might return a JSON body with an errors array. Inside that array, each error object had a code like 215 and a message like bad authentication data.
Okay, so a list with a code and message, no detail maybe.
In that specific example, yeah, not much detail. And interestingly, they used a custom code, 215, rather than just relying on the HTTP 401 status.
Hmm. And Facebook.
Facebook's Graph API example for a failed request to get an access token, maybe missing a parameter, returned an error object. Inside that object, there was a message, a type, like OAuth exception, a numeric code, and also an internal FB tree seed, which is likely for their own internal logging and debugging.
So different structures again. Facebook used type in code like RFC 7807 suggests, but nested it differently.
Exactly. It shows that even major players have their own conventions, sometimes developed before standards like RFC 7807 became widespread, or tailored to their specific needs. The key takeaway, though, is that they do provide structured error information beyond just the HTTP status code.
Right. It seems the goal is always to give the developer something concrete to work with, even if the exact format varies, though aiming for specificity and maybe RFC 7807 is the ideal.
That's a good summary. While implementation details differ, the trend is definitely towards providing more informative, structured, and hopefully standardized error responses. It just makes life easier for everyone using the API.
Okay, excellent. We've covered getting in securely with authentication and how to clearly signal when things go wrong with error handling. What's the last major piece of this puzzle we wanted to tackle today?
That would be API versioning. This is another really critical aspect, focusing on how you manage changes to your API over time without, well, breaking things for the people already using it.
Versioning. Because APIs don't stay static forever, right? They
Exactly.
need to evolve.
Exactly. You'll want to add new features, maybe improve performance, fix bugs, or sometimes even make fundamental changes to how data is structured or how endpoints behave.
And if you just change things, people's apps might suddenly stop working.
Precisely. Especially if you make a breaking change, that's a modification that isn't backward compatible. If an application was expecting the API to work in the old way, and you change it without warning or a versioning system, that application could just break. Imagine the chaos.
Yeah, not good. So versioning is about managing that evolution gracefully.
Exactly. It's a system for introducing changes, particularly breaking changes, in a controlled way. It allows consumers of your API, the developers building apps against it, to continue using an older, stable version while giving them the option and the time to migrate to a newer version when they're ready.
So it's like creating different tracks or timelines for your API. Older apps stay on track V1, while new development can happen on track V2.
That's a great analogy. It provides stability for existing consumers and allows the API provider to innovate. But, crucially, it needs clear communication. You have to tell people about new versions, what's changed, especially breaking changes, and when older versions might eventually be retired. Pushing changes silently is a recipe for disaster and unhappy users.
Okay, clear communication is key. What are some of the recommended best practices for actually managing these API versions effectively?
Well, first, try to maintain backward compatibility whenever you possibly can. Avoid breaking changes if there's a non-breaking way to achieve the same goal. It just makes life easier for everyone.
Makes sense. Don't break things if you don't have to.
Right. Second, document all your API versions thoroughly, not just the latest one, and publish detailed changelogs. These are vital for consumers to understand what's different between versions and decide if and when to upgrade.
Changelogs like release notes for the API.
Exactly. Third, try to avoid changing existing endpoints or drastically altering the structure of existing responses. If you need new functionality, add a new endpoint. If you need to return more data, add new properties to the response. Don't just change existing ones in a way that might break clients expecting the old format.
Additive changes are safer.
Generally, yes. Fourth, a very common and often recommended strategy is to version through the URI path. We can talk more about that. And fifth, publish a clear release schedule and deprecation policy. Let consumers know your plans for future versions and when older versions might be phased out, giving them ample time to adapt.
Okay, that all sounds very sensible. You mentioned versioning through the URI path as a preferred method.
Hmm.
What does that actually look like in practice?
It means putting the version number directly into the URL for your API endpoints. So instead of just EPA products, you'd have something like a PIV1 products or a PIV2 products.
Okay. I've definitely seen that V1, V2 in URLs. Companies like Facebook, Twitter, Airbnb use this, right?
Okay. Yes, many major API providers use this strategy. It makes the version explicit in every request.
What are the main advantages of doing it that way? And any downsides?
The big advantage is clarity. It's immediately obvious which version of the API a client is targeting just by looking at the URL. This also makes it relatively straightforward for the server to route requests to the correct implementation for that version, allowing you to host multiple versions side by side.
Hmm.
It can also help with caching, because the URL itself is different for each version, so caches won't accidentally serve v1 data for a v2 request.
Okay. Any cons?
Well, some argue it pollutes the URI, making it less purely representative of the resource itself. And if you have many versions with significant breaking changes, it can potentially lead to a larger code base on the server as you maintain the logic for all supported versions. But generally, the explicitness is seen as a major benefit.
What are some other ways people handle versioning, if not in the URL path?
Another common method is using query parameters. So the URL might look like apaproducts.version1. The pro here is it's pretty simple to implement, and you can easily default to the latest version if the parameter is missing. A potential con is that it can make routing logic on the server slightly more complex than path-based versioning.
Any others?
You can also version using custom HTTP headers. The client would send a header like accepts version 1.0 along with their request to AP products. The main advantage here is it keeps the URI itself clean, free of version information.
Right. So UR path, query parameters, or custom headers seem to be the main options. If you're setting up versioning, what are the essential steps involved? How do you actually implement it?
It really starts with planning. You need to decide on your strategy, early URI path, headers, etc., based on your API's complexity, your audience, how often you expect changes.
Hmm.
Consider using semantic versioning major.minor patch, where the major version, like the v1 in the URI, indicates breaking changes.
Okay, plan first.
Yeah. Then manage the changes carefully. As we said, aim for backward compatibility. Have a clear policy for how and when you'll deprecate older versions. Maybe use an API gateway to help manage routing to different versions centrally. Documentation.
Absolutely crucial. Keep documentation up to date for all supported versions. Provide clear change logs and maybe migration guides to help users move from one version to the next, and communicate upcoming changes well in advance.
Right. And deploying new versions.
Think about a gradual rollout, maybe beta testing. Gather feedback. It's usually necessary to support multiple versions concurrently for a transition period. And make sure testing is thorough for each version.
Okay. Monitoring, support.
Yes. Monitor which versions are being used so you know when it's safe to retire an old one. Offer support to help users migrate. And automate as much as possible. Automated testing for each version, automated security checks, integrating versioning into your CI/CD pipelines.
Seems like a lot to manage. Are there tools or libraries that can help with all this? Oh, definitely. Tools are essential. API description formats like OpenAPI, formerly Swagger, have built-in support for defining and managing different versions of your API spec.
Okay.
Platforms like Postman are great for testing different versions. And API management platforms, Apigee, AWS API Gateway, Azure API Management, Kong, and others often provide features specifically for handling versioning, like routing requests based on the path or header, managing deployments, and providing versioned documentation portals.
So tools can definitely ease the burden. The core idea, though, seems to be about managing change responsibly so you don't break things for your users.
Exactly. Versioning is crucial for letting your API evolve and improve without disrupting the people who depend on it. Communication through those change logs and documentation is key.
And that URI path method seems like a pretty clear and popular way to signal which version is being used.
It's explicit, well understood, and generally a solid choice, yeah.
All right, great. So to wrap things up then, we've taken a good look today at really 3 critical pillars of robust REST APIs.
Yeah.
The gatekeepers of authentication.
Making sure the right people get in.
The importance of clear error signals when things inevitably go sideways.
Telling people what went wrong, helpfully.
And the roadmap that API versioning provides for managing change and ensuring future compatibility.
Exactly. Getting these 3 areas right, authentication, error handling, and versioning, is what really elevates an API. It leads to systems that are more secure, more reliable, and frankly, much more pleasant for developers to actually use.
Yeah, it avoids those common pitfalls and frustrations and fosters a much better developer experience overall.
Definitely. It's about building solid foundations for communication on the web.
So as you're listening to this, maybe take a moment to think about the APIs you interact with every day, or perhaps the ones you're building yourself. What is the way an API handles its errors or manages its different versions? What does that tell you about the care, or maybe the philosophy, of the organization behind it?
That's a great question.
And maybe more importantly, how can you take these insights about clear authentication, helpful errors, and thoughtful versioning and apply them to build APIs that developers will actually love to use? APIs that feel like reliable partners rather than obstacles. Something to think about. Thanks for taking this deep dive with us.